So welcome back. We are now going to deal with theoretical parts. I'm going to actually alternate with theory and practice, right? So part 2 is going to be theory. Next week, there will be practice. It's how you actually do it using SQL. In the week after that, I will do theory again with the relational algebra. And then we will do practice again with how SQL actually implements this and so on, right? So just to have a bit of variety in what we learn. All right. So in terms of data models, we saw that there are shapes, 5 of them: tables, cubes, trees, graphs, and unstructured data or text. And we are focusing on tables. Cubes we'll see at the end of the semester. All right. So today, the goal is to define this mathematically as a mathematical object. It's actually pretty powerful because once you have defined it mathematically, you can even start writing theorems and deriving things on them. And we will actually do this in a few weeks. There's something called database design theory based on this. But today we will define things. So we need to define something that's called a relational table. We will see that relational actually comes from the mathematical concept of relation. So this is why some people call them relations. So you might hear sometimes table, you might hear relation, you might hear relational table. It's all the same. That's really all the same. Even I might use them a bit interchangeably, so don't let that distract you too much. So this is what we do today. And in 2 weeks, with theory, we will look at how we manipulate tables. Just like, you can manipulate numbers, matrices, vectors, all kinds of things. And it turns out that mathematically, you can also manipulate relational tables. So why tables? I think I motivated that already last week. This is because everybody's familiar with a table and we've known them for thousands of years, and even our ancestors would naturally put things like this on their clay tablets, right, for the inventory. And in fact, if you abstract a little bit, that didn't really change in 4,000 years, right? Maybe now you can swipe. You couldn't swipe, obviously, on a clay tablet. Now you can, but the way it looks is the same. So Edgar Code had the wonderful idea of saying that now users should see tables and they should be shielded from the actual physical storage, which could be a clay tablet as much as files and directories. And that's called data independence. All right, so now, before we do the math, I have to ask for what I want. I need to define on the high level the prerequisites, what I want to manipulate on the high level, and then we'll turn that into math. So what do you see on a table? You probably see that there are rows and there are columns, right? So this is pretty much the concept that we want to capture. So I'm going to give you plenty of synonyms of these primary concepts. So whenever you define a model, a data model, you need to pick what is called a primary citizen. A primary citizen is a concept that is central to your model. And then there are other concepts that you can add up top, but they are more secondary. So what are our primary citizens here? Well, there's the concept of a table, which, as I said, can be called relational table, or also collection, which is kind of a generalization. Then we have the concept of a row in a table. It's also called a record, a tuple, a document, an entity, an item, and business people call that business object. I actually love that. This is kind of a cool name also for rows. So a business object. I also will use them interchangeably. So I might say record, I might say tuple, I might say row. It doesn't really matter. That's all the same, right? Okay. Is there a question? No? All right. Then we have the notion of attribute, which is a column of a table. So you might also hear the name field or property or even key. Sometimes in the concept of document stores, that might be called a key. And one of the columns, can also be several of them, but let's start with one, can be special. It can be special because it identifies the record. For example, if you're the tax office and you have the database of all, let's say in the canton of Zurich, all of the tax residents, then the tax office has, I think they use the social security number or variation of that they call the register number. But basically, this is how they identify you. So if you appear as a record in their database, pretty sure they use relational databases too, then you will have this social security number that uniquely identifies you. This is called a primary key. In that case, it's just one column, but it could be several. You could also have multiple, like for example, the cars in Switzerland. It's the canton plus the number. So here you have two columns to identify a car, right? So this is the concept of a primary key, and you will work a lot of them in the database design theory course. Be careful because again, key can be ambiguous. If you just say key, it can be any column in the context of document stores or JSON, or it can mean that you have a primary key that identifies a record, right? For whom is that clear? The conceptual level? That should be easy, right? Okay. And now we have the concept of a single cell, or a fact, or sometimes called a scalar. Scalar is a bit of an analogy, if we have mathematicians in the room, the notion of a scalar in a vector space. So you differentiate between a vector and a scalar. Here it's a little bit the same. You differentiate between something that is structured, that is a table with rows and columns, and a scalar that is just a value like this, that we'll call an atomic value, all right? Okay. And now, for my mathematical definition, I have a few constraints that I need to put. I want a few things to happen. The first thing that I'd like in my relational table is for the names of my columns, also called attributes, to be unique. I don't want to have twice the same name. So customer ID, I do not want to accept that. That's not okay, right? So they must be unique. Then I want something else. I would like, at least in the original relational model as it was presented by Edgar Code in 1970, I would like the order of my records not to matter. I don't want this to matter. So it means, let me take this first because that's what I'm talking about. I want the order of the records not to matter. So if I reorder the records, I move them up and down, the records. So you see, instead of starting with Einstein and Ramanujan and so on, I start with Gödel and Ramanujan. Mathematically, I would like them to have the same meaning, to be the same mathematical object, right? This is what we call the set semantics of the relational model, if we say that the order of the tuples doesn't matter. Something else here is that the tuples are also unique in the set semantics. I cannot repeat a tuple. Now, what about the columns? So this is about reordering the rows, right? But if I reorder the columns, so here I swapped first and PID in that case, I also want this to be the same. I don't want the order of the attribute to actually be relevant, right? So this is something that I want on the logical level. So if I swap both of them, the table on the left and the table on the right are exactly the same thing mathematically. They are equivalent. For whom is that clear? Okay. All right. Again, I wrote set semantics in parentheses because some people like to change that a little bit and extend the model to not only allow for set semantics, but something that they call back semantics. Back semantics just means that now you're allowed to repeat records. So you see now I have two Ramanujan Srinivasa India, and I again have two Ramanujan Srinivasa India right there. And I'm also, so here and here, and I'm also repeating 4 Curie Marie France here and here. This is called bag semantics, right? So you can repeat multiple times the same record, and the number of times that it is repeated is important in the bag semantics, right? But the order is not important. I could swap now the rows or reorder them. That wouldn't matter as long as the number of times each record appears is the same. This is called bag semantics. And there is a third one that's called the list semantics of the relational model, where the order of the records actually matters. So in the list semantics, I want these tables to be different because the order of the records is not the same, right? So you need to just be aware, set semantics, back semantics, list semantics, there are 3 different views. And in the exam or in the exercises, we will always tell you which one we assume, if it makes a difference. Yes? Yes, in the list semantics, you can also have repetitions. Yeah. Even though it's actually quite common in practice now, if I say a bit in practice. So in practice, PostgreSQL supports the list semantics. So the order of the records in PostgreSQL will be important. However, there is a reason why you will not have repetition of the records is because you can have the list semantics with a primary key like this. So if you have a list semantics with a primary key, the order is important, but because of the primary key, you cannot repeat them, right? But it's still considered the list semantics, all right? And of course, if you have the back semantics, that excludes any concept of primary key right here because you repeat, okay? So ideally, when I do the math and turn that into mathematical objects, I would like to have all of that, right? I would like the order of the attributes not to matter. I would like the possibility to have all of these three semantics in a way that kind of is elegant in the mathematical framework that I can easily swap between the three. Also, just so that you know, a relational can also be empty, right? You could also have just nothing in there. That's totally fine. In fact, this is how you start. If you create your relational table in PostgreSQL, it's going to be empty, and then you add the data. It could also have just a single record. That's totally fine too. Okay. And now I would like also something else, ideally, in my mathematical abstraction of the relational model. I would like the ability to speak about some sort of rules that must be respected. And I need to speak about them in a way that is mathematically captured. These three things that I want to enforce in a relational table are domain integrity, atomic integrity, and relational integrity. And I'm going to explain what they actually mean. I'm going to start with the easy one, the relational integrity. So this is a relational table. Actually, it fulfills all three. But let me focus on the relational integrity. When you have a table like this, how many records are there in there? 3, right? I can actually split them like this, right? I could actually make each record explicit. So I have a first record, second record, a third record. And I just add the attribute names to every record to make it clear. So you see that this is the same, right? Here I see really the table with the individual records, and here it's grouped together. Now, this fulfills relational integrity as opposed to this, which doesn't. And the reason here we do not fulfill relational integrity is that there are places with extra attributes. For example, this here, that is an extra attribute for the third record, and this one is missing. And on the second record, I'm missing here a value for last. So the relational integrity is broken. So I can still view the individual record, right? But they don't have the same attributes, right? So I broke my relational integrity. So basically, when you break relational integrity, it doesn't even look remotely like a table, right? It's just a mess. This is a table. So it has to be the same attributes to have relational integrity. Okay, for who is that clear, relational integrity? Okay, so normally if I give you plenty of records, you should be able to tell me if it fulfills relational integrity or not. Okay, that's the first one. Now let's go to the second one. The second one is called atomic integrity. There is a second name for it that's called first normal form. It's the same thing. In fact, it's first normal form because we'll discover in the database design theory lecture that there is a second normal form, a third normal form, a 3.5 normal form, don't ask me why, a fourth, a fifth, and a sixth normal form. But this is the first one, and it's also quite easy to get. It's called atomic integrity. But again, just like for the relational integrity, I think it's best that I show you a counterexample for you to understand what it means. This is a counterexample. And you can see here that we have tables in tables, right? We have this big table over there, and then we have 3 tables that are nested. It's called nested inside the cells. It's like the Inception movie, right? A table in a table in a table in a table. So when you allow for that, then you're breaking atomic integrity. You're breaking the first normal form. This has again to do with the notion of scalar, right? This notion of scalar value or atomic value. We only allow for atomic values in there. I can have numbers, I can have strings, I can have dates, I can have booleans, plenty of things. I cannot have anything that has a structure, right? I'm showing tables here. There are other things that you could put in there that would have a structure and not be atomic. So here, atomic integrity, and here, broken atomic integrity. For whom is that clear? Okay, so if I show you records, normally you should be able to tell me if it's broken or not. And the third one, the third rule that I want to enforce is domain integrity. Domain integrity is something about the columns. Within the same column, I would like some consistency in the value that I find there. For example, the first name and the last name, I would expect them to be strings, right? String, who heard of string, the concept of string? Because that's something that computer scientists use all the time, but not everybody might know what this is. It's just text, right? That's what they call text, a sequence of characters. So the name and the first name, the last name and the first name must be a string. Physicist is a Boolean. You're a physicist or you're not a physicist, so true and false. And year should be an integer, 1905, 1936, 1842, okay? So this table has domain integrity. Why? Because I was able to find for every column some type that all the values in the column share. It cannot be any type because I could cheat, right? I could say, okay, no matter what I see, I can just take as the type of everything, right? And that's always going to be true. You cannot do it like this. It has to be what the computer scientists call an instantiable type, the sort of types you have in a programming language, like integer, double, string, and so on, something you can actually instantiate. So you cannot cheat the whole thing saying it's the type of everything. So if you can find types like that, you have domain integrity. In that case, it doesn't work. And can you see why? For physicists, I have Booleans and I have an integer too. So here you cannot put Boolean, you cannot put integer, it just doesn't work. You could put the type that has everything, of course, but again, that's cheating, that you cannot do. And again, the year, you see there are two integers, and then there is this 42, which is technically a string, right? So again, here, you could again say the type of everything, or you could say the type of anything that remotely could be converted to some integer in a way that makes sense. But again, that's cheating. You really have two integers, and then you have a string. So that doesn't fulfill domain integrity. Who understands? Okay. And in that case, I was able to do it, right? Given these three records, I was able to put string, string, Boolean, integer. So that's domain integrity. Okay. Yes? Mm-hmm. So indeed, you're absolutely correct that you could here use something called the cast, which is you could force the -1 to be converted to a true. So anything that's not 0 would basically be true. You could also technically even implement things that clean up the 42 as 1942 or something. But it's not part of the model when you do this. The model is really in terms of math, you really have values, and mathematically -1 is not a Boolean. It can be cast to a Boolean, but it's not a Boolean. And here I'm really doing the math. In the implementations, you're absolutely correct that when you use a system, you might have some PostgreSQL or some implementations that will still convert it for you. If you give them this, they will still be able to change it to a Boolean. However, the reason it works is that you design the schema in the system where you said that you expect a Boolean, right? So you're still forcing something in the system. You're still saying, I want a Boolean. And then when you turn this -1 into a true, it's just the system being nice to you. It could throw an error, but actually it's elegantly saying, okay, I'm not going to throw an error, I'm just going to convert it to a true. That's kind of what happens. Does it make sense? All right, do we have a question on Zoom? No, okay. Ah, okay, awesome. Oh yeah, we should actually use the microphone, I forget, yeah. It's just that sometimes it does the Darth Vader voice, so you try to speak in it and then nobody can understand. But anyway, okay, so here it's broken because unless I take a hammer and force my way into converting everything to the same type, it's not the same type right here. All right. So let's come back to these three rules. The idea is that a relational table has to follow these three rules. Right. So basically a relational table and the beautiful world of SQL is right here in there. But I also want my model to be flexible enough ideally, to be able to drop the rules if I want. Why do I want that? Because that's what we will do in Big Data for Engineers next semester. In Big Data for Engineers, we'll start actually dropping these rules because that's the beautiful world of NoSQL. Who heard NoSQL? Some of you? It means, so of course you can still change history, but technically it's supposed to mean not only SQL and not NoSQL, but that's a detail. And so in Big Data for Engineers, we'll see that we will even look at data that doesn't have domain integrity, that doesn't have atomic integrity, that doesn't have relational integrity. But in this course, we want to be at the intersection of the three. And so if I add one more requirement to my mathematical definition, it would be kind of nice if mathematically I have an easy way to just switch it on or off, right? That I can switch these three on and off as I want, right? That kind of would be a nice feature. All right. So now if we want to do it mathematically, it's like cooking now. What do I have? I have attributes and values. And I just want, so now it's in a row thing, just got them like this, and I want to assemble them in a mathematical thing that would be a relational table in the sense that it fulfills all of my requirements that I have explained in the past half an hour. All right. So now that I have explained to you my high-level expectations of what I want for a relational table and the kinds of features I want from the math, we can go to the math. So in order to do math, I have to take into account that you in the room and on Zoom and binge watching, you come from everywhere at ETH, right? We have mathematicians, we have physicists, we have mechanical engineers, we have electrical engineers, we have people, climatologists, I was looking for the term. So you have plenty of different backgrounds. So you might not all know the same things, or if you do, you might have then seen them a long time ago. So I want to just brush up a little bit. So I know the mathematicians are going to be bored because this is obvious, but I want to make sure that everybody is really following what I'm about to explain here. So in mathematics, we have the notion of a set. It seems simple because it's basically about like some sort of a box in which you put objects, and then an object can be or not be in the box, right? So a set is actually defined based on whether or not you are in the set. An example of set, so here it's just abstract, I call it A and I put four objects in there. An example of set is N, the set of natural integers, right? 0, 1, 2, 3, and so on and so on. All right, that's an example of set. And 1 is in the set, -1 is not in that set, right? So this is what it's based on. Now we have a string, the set of strings. I call it S. It's not a standard notation. This is standard. Everybody would know what that is. Here, I'm just calling it S in that way just for the purpose of the course because I'm going to use these strings. So these are examples of strings, right? So we put them in double quotes like this. So the first one is the empty string. There's nothing between the quotes. And then you have foo, bar, ETH Zurich, database systems, the complete book. These are examples of strings. Foo and bar, you might actually see a few times. That's because I'm a computer scientist, and computer scientists, when they don't know what to call something, as an example, they call them foo and bar. I think it comes from the German furchtbar, that somehow it was heard that way, like foo bar, and then it became foo and bar, right? So this actually comes from the German language. But when you see foo and bar, that's just that you put stuff in there that just doesn't matter, just to give an example. All right? Okay. Now, you have this little symbol that looks like an E that says it belongs to the set, or it doesn't belong to the set, then you cross it, right? Now, it sounds very trivial, but in the 19th century, the mathematicians had an existential crisis about that, and some even committed suicide because of that, because it seems simple, but it's extraordinarily difficult. Because when you start talking about sets in that way, from an abstract perspective, and then you might be tempted to say, okay, let's define the set of all sets, right? There's no reason why they shouldn't exist, right? And then you start, because when you're a mathematician, I love math as well, I love to do these kind of things, then you might think, okay, if you have a relation like this, maybe I could have something that is contained in itself, like X belongs to X, I belong to myself. The set of all sets should belong to itself because it's also a set, right? Then you can say things like, the set of all the sets that belongs to themselves and the set of all the sets that do not belong to themselves. And then you run into all sorts of very scary contradictions that basically, yeah, it's a disaster. This is actually this slowly led us to Gödel's theorem and the idea in the 20th century that technically there is always room for creativity and inventing new things, and you cannot just automate and catch everything in a mathematical framework like this. So you cannot automate proving in a general way. But anyway, let's get back to this, just to say it looks simple, but be careful about these things. Here is an example of an integer 1 that belongs to the set of natural numbers. So 1 belongs to n. Here you have an example of a string foo that belongs to S, the set of strings. Next, you might have two sets, and one of the sets is a subset of the other. It just means that all of the things that are in B, they're also in A. That's what a subset is. For example, the set of the students who study mathematics at ETH is a subset of all of the students of ETH, right? That's an example of subset. And typically, it's written in this way with this cup that seems to have been spilled over on the side. So B is a subset of A. And the little bar on the bottom just means that technically it could also be A, right? So a set is also a subset of itself. So the set of all students at ETH is a subset of all students at ETH. So that's kind of like an equal possibility. Okay, so we have subset. An example here is that all of the even numbers, that's a subset of n, right? Any even number is also a natural integer, right? I just said even numbers. I, of course, means the ones that are non-negative. All right. So this is another example of subset. Everybody's following? Okay. So now another example is all the names of all the universities. That's a subset of the set of strings. So ETH, Stanford's, EPFL, and so on. Now, there's convenient notations that mathematicians have in order to denote the standard sets. The first three, everybody agrees with. So B is the set of the Booleans. It's actually very small because it only has two elements, true and false, even though you can cast other things to them. Then D is the set of all decimals. So decimals is basically all the numbers that have a finite, that can be written with a finite number of digits in base 10. So these are called the decimals. Then you have n, that is the natural integers, so non-negative integers. And then S, V, and T is just for me for the course. This is not something that would be universal in any way. So S I use for the strings. V as value I will use to denote the values. Depending on the context, it might be anything or it might be atomic values specifically, right? And then T I tend to use for the relational tables. So what we are trying to define here. All right. So now this notion of sets, that's something that I've already mentioned, can be generalized to the notion of a bag. And a bag is just the same thing as a set, except you can repeat occurrences. In a set, you cannot have multiple times the same element. In fact, the reason is actually simple. It's just that you define a set with this belongs to or doesn't belong to, so you don't capture the notion of multiple times. Yes? Yes? Oh, I should have called that natural integers. You're right. So Z would be the notation for including the negative ones. N is I will change it. That's the natural integers, the non-negative ones. Yeah. Then you have N star if you want to exclude 0, Z for all of them, and so on. Yeah, absolutely right about that. Yeah. All right. Are you a mathematician? Okay. All right. So yeah, these are just a few examples. Okay, now I have the notion of sets. Either you belong to a set or you don't, so there is no notion of repetition in there, but then you can also define bags. And in a bag, you also have the notion of a repetition. So you could say that, for example, the colors are really close to each other. Apologies for that. Let's talk about the blue ones. So you see that there are two blue circles in there, right? So it's repeated. In a set, either it's in there or it's not, but in a bag, you can also say it's two times, it's twice in the bag. So that's a bag. Maybe mathematicians don't use bags that much, but computer scientists love them. Then we have lists. I'm using the computer scientist term because mathematicians, I think they call them sequences, but computer scientists, they call them lists. It's just, you're just listing the elements in there, and we're going to take a break for 15 minutes, and then I'm going to take it from here. All right, so see you at 11:15. You deserve it.